start recording, and I will come back, but you guys can start with.
Okay, let me fix this camera. Okay. We're doing postulates of quantum mechanics. What's a good chalk? This is a chalk. So I'm gonna go by coincidentally, I think it was like chapter 3, section B. So I'm basically just doing the entirety of that. I'll just in time. Okay. Let's start off with postulate 1, and I don't want to write postulate 1 for P1. So at time T0, let's say all this system is described by a the book does not say normalized, but we're just going to assume it's normalized basically for reasons. They use normalized later, so they just don't write it in their P1. Normalize vector, also called a ket. Call that ket psi up around T1. Okay. In a state space H, H is a Hilbert space, which is a complete inner product space. So we can find inner product of this. Okay. And like just a side note I'm going to add is this idea of it being in a vector space means that we can kind of add them together and it means something, which will be used in about an hour probably. Okay. Any objections to P1? Have I done anything wrong? Complete. Good question. A useful property. Generally speaking, it's kind of like the thing where Cauchy sequences converge. Whatever that means here exactly. The notion of completeness applies to, I think, any metric space. Okay. Every physically measurable quantity is associated with an observable, also, which is just a self-joint linear operator A that maps from Hilbert space to itself. And then we will, P3 will discuss what this observable is actually good for at all. This way. Okay. The results of measuring the physical quantity associated with A is always an eigenvalue of A. So what we're saying here is basically, if I want to measure something, I can pick some linear operator that will call the observable for that physical quantity. For example, momentum or energy, given an excitation system. And then if we ever decide to measure momentum or energy, what we get is always going to be some eigenvalue of this operator that we've chosen that works. Okay. How is anything wrong? People are thinking QM. I think QM.
The operator unique
unique
for each
The observable is the operator. Okay. Like each physical quantity. Mm-hmm.
And then you call it a momentum operator.
Mm-hmm.
And then its action, let's say, gives you the momentum eigenvalues. Then is this operator unique?
It's a good question that I don't know the answer to.
The answer is these operators are unitarily, it means they're related by some unitary transformations. So
Okay.
you can choose different operators to have the same action.
Okay. Because it's a useful property to have, so we'll be taking many linear combinations of things. I'm not 100% sure as to why I did not have a lot of time for this. Hi, Ivan. You want to answer a question from Sylvia?
Maybe do you want to?
Okay.
What's the question? Give the cup to someone. You don't have to have tea. That's mine.
What is completeness good for here?
Oh, completeness. Oh. So I have. Okay, that's a good question.
You want a mic?
About completeness. No, that's fine. I'm loud enough.
Okay.
Talk about completeness. I realized whatever I was saying last time was completely wrong about completeness. So it's yeah, essentially I'm not sure. And there's actually some people who have recently looked at yes. So you have a Hilbert space. You want your vector inside the add up to some other vector which is some linear combination. But this linear combination we usually only see it as like, some finite number of vectors added up together. But in a Hilbert space, which is infinitely dimensional, we may have like operators with like infinite dimensional matrices. So when you have like linear combinations, you might have like an infinite sum of vectors, which is not necessarily inside the Hilbert space from here. So yes, okay, maybe one of the better things is that you might have Hermitian operators. So okay, you might have like Hermitian operator. So you have your Hamiltonian, which is the energy operator, right? And maybe it will have some eigenvalues, it will have some bases. Okay? But then maybe you'd have some other measurement that you want to do, which could have some other Hermitian operator. And that would have its own eigenbasis, right? And you would want to write vectors in that eigenbasis of that other measurement in terms of the energy eigenbasis, right? And we'll see why later. But maybe those rewriting that basis in terms of this new basis might not be, like a nice kind of finite linear combination. It might be some more complicated linear combination. And so you need some condition that tells you how to roughly deal with infinite linear combinations. Well, because so in one basis the Hamiltonian is diagonal, and you know the eigenvalues the Hamiltonian. In another basis, this operator, this other measurement related matrix is diagonal. Okay? So if I want to, the Hamiltonian is important because it appears in the Schrödinger equation, and you need it to see how things evolve in time. But then maybe I want to see, how this measurement. What will I measure for this measurement after some time t? Okay? So I'd want to maybe rewrite that in terms of this basis, and for that to work out nicely, maybe somehow I would need to look at some infinite combinations. So maybe there'd be some operator to find the eigenvectors of which I would need to take some infinite combination. Yes.
And these are some conclusions what's in the Schrödinger book we use, we say that like we call Hilbert space. Basically it's a space of functions whose integral of norm squared is convergent.
but that is not sufficiently general because you don't always work with wave functions. Right? In optics, for example, you have a lot of these two-level systems, which are just you have like some polarization up, polarization down vector, and that's it. And okay, those aren't wave functions necessarily. You don't need to know that they're wave functions.
I understand. I just mean like would it be like a name thing?
No. Well, you can show that L2 is a kind of perfect space almost. So not quite. Like completeness is an important property, and there's actually one paper that came out in the last like 5 years that discusses this, and I haven't read it, but I know it exists. So this is a good question. I don't have necessarily faith.
What I understood from what you said is that you just operate on basis. They're going to operate in a different.
Maybe not exactly. Maybe this will be useful for finding the eigenvectors of some more complicated operator. And the eigenvectors of that operator might be some infinite combination of energy eigenstate. And you would want to make sure that things converge properly. So I don't have a good answer. That's the best answer. Yes, but you didn't say it in terms of I have another method.
Okay, are you done? I've just been taking the notes because I'm very slow. Okay, so postulate 4 has like 3 different forms in the book, so I'm going to call this one 4.1. So the general goal of all the postulate 4s is that we want to find, because I said every single possible measurement is some eigenvalue of A. So we want to find the probability of finding any particular eigenvalue. That would be a convenient thing that we would be able to do. So this particular case, 4.1, we let the spectrum of A be non-degenerate, so no eigenvalues are repeated. Then for all n, I've called each of these eigenvalues lambda sub n. There's going to exist a unique upscaling eigenvector u sub n with eigenvalue lambda sub n. We're going to let this one be the one with norm 1 because it's convenient. Then we can write this. So where any vector at psi can be written as a linear combination of these eigenvectors for some constant Cn. So this is just a linear combination. So our actual postulate is going to be that C sub n is in fact going to be equal to this inner product. Okay. Because physics versus math convention. If I write this, I'm going to have it be linear in the second entry.
You're right, a little smaller.
A little smaller.
I can see this too well.
Yes. Okay. Fair enough. If I write a comma instead, I'm going to mean that it should be linear in the first entry. What?
That's actually a good idea.
No. I got confused when reading the book, so I just said, okay, I'm doing this now. Okay. So, where was I? Yes. Okay. And the probability of measuring lambda sub n is going to be the norm of C sub n squared. Okay. Which is like, by definition equal to this stuff up here. Okay. Okay. Since we decided, where is it? All the way over here, that the ket psi is going to be normal, we do have that this is just equal to 1. And also, in fact, that the sum on all n of p lambda sub n going to be equal to 1 because this is kind of the same thing. Is this not immediately obvious? Why not? So we do this, and then inner product. Enter, you know what, maybe I'll just write this all out. I'll do this over here so that I can write more things later. I'm going to write it with a comma because that's the notation I actually know how to do math in. Okay. So then we can write not with that. I feel like I'm almost writing too large now. But... Okay. So I do things. And then I will simply take the sum up because that is something I am allowed to do, really. I should call these, I could index these differently. I'll call these all these sub m. So then I can pull the sum and pull the sum again. Okay, and then I don't want to bother writing all the lines, so I'm also going to do this here, where I will just pull the c's out of here. Yeah, and then we will have where this is really just so inner product. This thing, because we took A to be self-adjoint, we're going to have that these u sub n, u sub m, they form an orthogonal basis. So this is actually just going to be equal to delta nm. So we'll take the sum over all of this. We're just going to get the sum over all n of c sub n squared. Does this make sense?
Your notation, but your own
Ah, yes.
doesn't matter.
Oh, yes.
Yes. Put a bar over a random one. I can't see which one is without
My bad handwriting. Okay. So this thing. That is the entirety of 4.1. So basically, again, this is the case where the spectrum of A is not degenerate. And also, sorry, I forgot to mention, it is also discrete, so there's not a continuous thing, which is what we would most be comfortable with anyway, but oh wait. My handwriting is terrible. Okay.
You'll probably say that. So here, because we have a discrete spectrum, right? We have some possible outcomes and measurements lambda n that we can compute, and so we can sum over the probabilities of getting each lambda n, right? Good. Now suppose the things that we could measure were somehow continuous, right? So for example, I could measure my particles to be, within some region of space. Right? So instead of having discrete possible outcomes, I have continuous outcomes. Okay. What happens to the sum? It becomes
Integral.
you can't deal with that answer.
True.
Yes. But essentially, the idea is what he's saying that we're going to have a different version of the postulate. The only thing that's different about that version is just you replace the sum over lambda with an integral d lambda, with the thing that we can measure somehow. And otherwise, the idea is exactly the same. So that postulate is not at all different.
Okay. Maybe.
Oh, sorry. One other comment that I wanted to mention. So why do we know that these vectors have to be orthonormal? Because by the spectral theorem, you probably said this before, but by the spectral theorem, because all of my operators are, so all of my observables are, so all of my measurements are associated with an observable, which is a Hermitian operator. And by the spectral theorem, actually, not even by the without the spectral theorem, you can prove that if something is an eigenvector, if there's two things that are eigenvectors of the same Hermitian operator with different eigenvalues, that those two vectors have to be orthogonal. And so this is an important idea in what sense is that in quantum mechanics, if I have two different things that give me two states that give me different measurements, these two states are somehow like completely unrelated to each other in terms of these probabilities. Okay.
Let me see. Let me think about how much I want to write up this. This is exactly the same thing, except you're now allowed to have repeated eigenvalues, so you can't just like say choose u sub n. So they do like funny double indexing stuff where they do like they start writing this, where if they all share the same n, then it's the same eigenvalue, and I is like different orthonormal vectors like that all still have this eigenvalue. You're allowed to do that.
Can you draw a picture for that?
I'm not sure exactly what.
So okay, you're saying that I have an operator and I have space, so that I can decompose this space into eigensubspaces. So draw a picture of that. Maybe. Draw a picture. So I'll draw it here.
That's fine.
So we have what? We have so okay, we have my vector space V. Okay? And I have some observable A. Okay? And so the idea is that okay, this has some basis of eigenvectors. And so I can kind of look at subspaces. You have probably seen these. This is so I of lambda, or I don't know, whatever division you want to use. This is all vectors V in my Hilbert space such that A of V is equal to lambda. Okay? So I just look at the subspace that has eigenvalue lambda under A. Okay? And this you can prove that this is indeed a subspace and whatever. And so the point is that if you have a Hermitian operator A, you can kind of split this into these eigen subspaces, where this is the eigen subspace for value lambda, this is the eigen subspace for some other lambda 2, so on and so forth. Okay, do you agree? But the point is that this subspace need not be one-dimensional. This subspace, I can have multiple vectors that have the same eigenvalue. Do you agree? And yes, so this is one way to think of it, that a Hermitian operator with some eigenvalues, then these eigenvalues define like some partition of my space into disjoint subspaces. And the point is that you know that a vector from here has to be orthogonal to a vector in here. Right? But the problem is if I have two vectors from the same subspace, they might not be orthogonal. Right? Because okay, it's the same subspace. If I have the same subspace, I can always choose some vector like this and some vector like this. And they will somehow not be orthogonal. Agree?
Question is, why do you know that the vectors in different spaces are orthogonal?
Okay, let's check this. So suppose I have different eigenvalues lambda 1, lambda 2 with V and U as what does this mean? This means that H of H of V is equal to lambda 1V, and then H of U is equal to lambda 2U. Okay? Okay. So suppose these are okay. Sure. Suppose these are different, so at least one of them has to be non-zero. Okay. So let's compute the inner product between U and H of V. Okay. to, so nature v is what? Is lambda 1v. Okay? It's a real number. I can pull it out. U comma v. Okay? This is on the one hand. On the other hand side, this is self-adjoint. So I can take this guy and move him over here. That's my definition of being self-adjoint. That I can move it, in the inner product, and that doesn't change. Okay, now I can move this to the other side and have HU comma V. Okay, well, this is now equal to lambda 2 of U comma V. Okay? Because I applied this to this, I got lambda 2 of U. This is an eigenvector with a different eigenvalue. So I got this has to equal to this.
Oh, wait, okay.
Do you see? Okay, but now this is the same number as this. And these are possibly different numbers. Okay, suppose that this one of them, if they're different numbers, then one of them has to be non-zero. Okay, because one is zero, the other is not. But this means that what? This means that lambda 1 minus lambda 2, inner product u with v has to equal to 0. Okay, well, this is non-zero because they're different. So this has to be 0, so u has to be orthogonal. But the point is that within the eigen subspace, that's not guaranteed. Within the subspace, things are orthogonal to each other. Okay, but within the subspace, it's a subspace. I can always choose an orthogonal basis. Okay, like this is a subspace, and then by whatever Hilbert's, the Gram-Schmidt theorem, I can, okay, maybe in the infinite dimensional case. Yeah, it works in any countable case. Okay, and then by Gram-Schmidt, I can then diagonalize this and make this an orthogonal basis inside of here. So that's yes. So here things have to be orthogonal between here and here. Within here they can be made orthogonal by this. And actually we'll see this idea again later where we can partition our space and then we further partition whatever's happening inside the box.
Okay, well, I'm just writing. So basically, we do take an orthogonal basis such that call this orthogonal basis. This will just be the thing I just erased. That okay. I'm just gonna call our observable operator A. So an orthogonal basis such that all eigenvectors, and this in particular is true for u sub n. What do we call this? U sub n power. Like, what do I even? How do I say this notation?
I know I vector.
Sure. Okay. I u sub.
Okay, so what is u sub n items?
This is the full orthogonal basis where the bottom index.
I have this here. So what is u sub n I in terms of this picture?
Anything that's u sub 1 something will live in here. Anything that's u sub 2 something will live in here.
No, not just live, it will span. So for example, write down the basis of I lambda 1. And write it into the diagram. Yes.
No.
That's not good.
You meant like draw a picture.
I meant like, so I have u sub 1, 1, comma, u sub 1, 2, comma, dot, 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 u sub some finite number 1. Okay. I really like it when people, I really like that making things too clear. It's too obvious.
Okay. Well, there we are. So, where was I? Okay. Then we can.
So we know we can't write such a basis.
Yeah. Okay. Then we write this is an expression that I really small. Okay. Wait, no. So our psi can be written as sum over all n, sum over I from 1 to dimension of e sub lambda sub, and I called this is what he called like lambda sub n, I suppose. And then I just do this for some constants c sub n I. Okay, so just the same idea.
All this is saying is that I have a basis and I
Yeah.
can write my vector in terms of the basis.
That's all. Okay. Then I think that is actually really interesting. Once again, p of lambda sub n is going to be equal to sum I dim e lambda n of the sum of the squares of c and I absolute value squared. So essentially just what I wrote here. But now there's more of them, so we add these together. We add the squares together. Okay.
So this is in the bonus, but you can then instead rewrite it.
Yeah, that's what I was about to do. I have like more lines here. Ditto.
Bigger.
Sure. Of that thing. So like these are the same. Okay. So then they go on to say like notice this probability should be invariant under some like, change basis. This probability should not depend on which orthogonal basis you pick. They do provide proof of that, which I did right down here, but I don't think.
Don't write that proof down.
Yeah.
Because it's,
I don't think I will.
that proof is like a little silly.
It's a projection, good enough.
Yeah, like that proof doesn't tell you anything.
Yeah.
You just show that change basis.
I'm gonna save the front board. Actually, I have to write things. I'll write on. I was gonna write like a summary of the process over here, so I'm just gonna leave things over there. So I'm just going to quickly write down the integral thing, which I don't fully understand and will not use.
I mean, sure, write it down. If you understand the previous stuff.
Continuous, non-degenerate spectrum. So basically, they say what I had said earlier, pretty much. So you integrate over your d alphas, where c is now a function of alpha, and they're now called v sub alpha for some reason. Okay. And they also define probability density dp of alpha. I believe that was a row of alpha. D alpha, where this quantity tells you the probability that you, in their words, more or less, you find something between alpha and alpha plus d alpha, which I don't fully understand.
What part of that do you understand?
Infinitesimals messing with my head.
Okay, it's just a probability density. That the point of all of this infinitesimal stuff is that if you were to integrate it over some region, then it will tell you the probability of you being in that region.
Yeah. Okay.
There's nothing deeper than that.
Yeah. So that is that pretty much. Okay. Also, average value / expectation value.
Before we talk about this, so let's briefly sum up what we've achieved. Right? So we have our Hilbert space, right? That is where our states are. So the state of my system is described by some vector in some Hilbert space. Okay. What is key about a Hilbert space? A Hilbert space has some inner product on it. Yes. Why is this inner product necessary? This inner product from postulate 4 extract the only information you can extract is the probability of making some measure. Okay, how do I do that? We have postulates 2 and 3, where anything that I can physically measure should have an associated permutation operator to it, where the eigenvalues of that operator tell me what can be measured in the experiment. Those tell me the thing I will see on the dial reading of my device, and the taking the inner product squared between my state and the eigenvectors tell me with what probability I will measure these things. Right. So state is a vector of a Hilbert space. The inner product is used to compute probabilities, and every physically measurable quantity is associated to an observable. And the eigenvalues of that observable tell me things I can measure in experiment. And so in physics 256, everything you've been doing is essentially that. You've been looking at some particular observable, and you were computing its eigenvalues to see what can be measured in experiments, and then you were using Bohr's rule, which is, I think, postulate 4, to see, to actually compute the probability of measuring this.
Okay. Expectation value, which I will not prove and we will not use again today.
Yes.
That's just like symbol for it, and it is given by.
So what is the expectation value?
It's the average value you should expect when you measure something.
What's the setup? What's the setup?
I have a thing I want to measure, and like on average, I measure a bunch of times, and I take the mean of everything.
What side? What side?
Oh, sorry. If you fix an initial state, and then you have a thing you want to measure from that initial state, if you set that up a bunch of times and measure it a bunch of times, this is the average of what you should get.
Yeah.
Not necessarily that you'll ever actually measure this.
Yeah. So if suppose my system is in state psi, and I want to measure whatever is associated to observable A, then if you wanted to compute on average what will come out of your experiment, you will compute this. You can verify that using those postulates, but okay, that's just for people to know this in case.
Okay, I'm now going to write things from right to left because I have planned poorly. Okay.
It's not too late to
I want to save that space so I can write down like everything really small.
you can erase it and write it however.
You can do this. That should be enough. Okay.
So you want to make smaller than that, maybe.
Yeah. So basically, the idea of this postulate is if we measure something and then we see that it takes on a certain value once we measure that observable and then we don't touch it. If we measure it again, it should have the same thing and not like randomly change for no reason. So in other words, the state has collapsed to be in a certain part of the Hilbert space where the only thing you can measure is like your lambda sub n, which is exactly just the eigenspace of lambda sub n. So basically the idea is when lambda sub n is measured, the state psi collapses to this thing. P sub n is not probability, it is a projection onto the eigenspace corresponding to n over the square root of this quantity. And they work this whole thing out of the book, and I will not. This is just a projection and we normalize it.
Yes. So let's look at an example. I'll just write down an example really quick.
Go for it.
So suppose initially my system is in some states of, I don't know, I have, okay, so suppose my system is this contrived thing where I have a light switch. Okay? And this light switch is a quantum light switch. And this light switch can either be flipped up, turned on, or turned off. Okay? And so suppose that I will have some observable related to seeing it on or off. Okay? And it will have two eigenstates, the on eigenstate and the off eigenstate. So suppose my initial state is something like this. It's some 50% of it being on, 50% of it being off. Okay? But suppose so that my initial system starts with this superposition. let's suppose I stop and actually look at the light switch and make a measurement, and I see that it's on. Okay, what is the state going to be? So measure it to be on. Okay, what is the state of the system going to be now after this measurement? Okay, you can't answer. I guess you can't answer either, and neither can you, so you have to answer.
It's the downstream.
To be on. Oh, okay. I guess whichever one is on. So it's just the upstate, and it has no coefficient in front of it because I want it to be normalized because now there's a one probability of me measuring it to be on. Right? In principle, like as I drew the thing before, I could have multiple states correspond to measuring on. Do you agree? I can have multiple of them. And so in that case, I will kind of have some expansion in terms of all sorts of states, and I will just only keep the ones that are in this eigenspace, just delete the rest of them, and then normalize it to be a blank one. Okay? And like Trevor said, this whole idea is a very physical one, where it's, well, if I have a, if I measure something, if I was to instantaneously do that same measurement again, I should measure the exact same thing, and there shouldn't be any probability to measure something else. So there's another particular experiment that is very relevant. Yes?
Yes. That I definitely had an original thought about myself and was not forced upon me by you.
Yes.
Double slit. So like
Question for the audience. Do people remember what the double slit experiment is? Okay. Well, how does it relate to this?
Like when there's like a photon and then there's like a double slit, and then if you like have a if you like if you don't measure it, there as the photon hooks which like split, you will have like a I don't know how to explain, but because like
Yeah, some pattern.
and then if you measure it, it will like have just one state, and then it will like have like just one.
Yes, exactly. So I'm kind of, do I make a measurement earlier or later? If I make a measurement at the screen once it hits the screen, then okay, it can do its interference thing, and this linear combination expands in some complicated way, and you get one thing. But if I measure that it passed through this slit or that slit, then okay, I know for sure it went through this slit, so the wave function collapses, and the probability is 100% that it will be just kind of a left or a right one, and that it doesn't interfere in any way. Okay, so that's like a direct that experiment is actually a direct consequence of this postulate. Or maybe this postulate is a direct consequence of that experiment. I don't know. Whichever way you think.
okay.
Okay. Yes.
I keep talking to keep... Okay. Maybe I'm gonna write P6 somewhere.
Do you want to do like a quick actually so logically, what are we still missing? So what everything we've talked about so far tells me what? Tells me. So far, everything has happened in what way? To everyone. Every question is to everyone unless you like obviously know the answer. So far, every single postulate, everything happened. How? Well, discretized, no, that's fine. We learned that if it's not discretized, you replace some with an integral. It's not too bad. It's the same idea. But yeah, so I would do this measurement, but what happens after? Okay, it's normalized, but everything so far has been happening instantaneously, right? I'm looking at everything so far in one instant of time. Physics, it turns out, things happen over time. So we need to introduce some other thing, which is P6, which tells me how to have my state evolve along time.
Okay. Start writing. Okay. So this is going to be the Schrodinger equation. I think I put X in my place. Okay, Schrodinger equation. So this will basically tell us how a state will evolve over time. And its statement is I H bar partial or just D?
Partial, I mean, whatever notation you choose to use.
Sure. I'm going to like switch notation immediately after this, which is a bit unfortunate. I don't know why I did that. And then this. Okay, so this is a statement. Present this. Well, I is I. H bar is Planck's reduced Planck's constant, and H of t is going to be our Hamiltonian of the system. Which will basically tell us this is the observable for the total energy of the system. So, okay. What am I reading? Okay. Yeah. Observable social total energy of the system. So this does things. So it was just going to be about solving if it's not state. So, I don't know if you want to say something before that.
Yes. So right. So yeah. Before everything happened in one instant of time, but now we have some differential equation which lets me figure out okay, what will the state be in the future if I know what it is now. I guess in some sense you can think of this from the people who have done the OES reading book. You can think of this as this is like kind of defining some vector field on my Hilbert space, and I can flow along this vector field at every point in time. Okay, that's just what an OE is. I didn't say anything. So, right?
Okay. If h of psi is equal to e sub, where e is just like some number. So I
well, why do we write this number as e and not lambda all of a sudden?
Because
no, I'm not asking you, I'm asking why. You know the answer. Yes, because h is the observable energy, so the eigenvalues have to be energy. Okay? I will never ask a complicated question. Yes.
Okay. Then we can solve. I'm going to simply write a thing down. Okay. Okay. Yeah. Then we can write basically. I thought that is terrible. I should not write to that angle.
Take a longer
No. Okay. Then we have a sum n of e to the negative I sub n over h bar a sub n I sub n. So we are once again this that is not a thing. This sorry, I forgot the t.
in the
Thank you. So this bit is just like from pretty much linear combination stuff, and this is so that the Schrodinger equation works pretty much. So if we just consider like this bit, if we take the time derivative of this, then this will come out. So then we have I h bar times negative I e sub n divided by h bar. The negative I over h bar just cancels out, so we get e sub n over here, which is what we wanted if we're dealing with phi sub n, which is an eigenvector, eigenstate. Then we get that, oh, this thing that I wrote down here. So this is just how can we get things.
So this is why the energy basis is important to expand. Why you want to expand things in terms of the energy basis, because then solving the Schrodinger equation becomes very, very easy. You just each basis thing and multiply by the right base factor. And that's what I was saying about like change of basis kind of matters, because energy basis is easy to look at time translations in energy basis, but then maybe I want to measure something that's not the energy, maybe it doesn't compute with the energy. So I need to know how to change from that basis into that other basis.
Okay. And then last time I'm going to write here. Since we're not dealing with time, it would probably be nice to know that where is it? This thing I wrote over here is actually true if we consider it as a function of time. so that we have probability adds up to 1, which is a good thing to have.
You want probability set up to 1 for all.
So take partial t of the thing I wrote over there. Okay, I'm just going to write this out.
Okay, well, perfect. The question
What? Okay, I'm going to mysteriously switch notation because it makes me feel better.
if you guys have to leave, that's fine. We'll hopefully end in the next, I don't know, 15 minutes. And you should, you're not even in the stream.
I've got the H.
Getting some E's.
Let me pull stuff out. I mean, I saw for joiners needs to wear the same thing, so this just goes to 0. The whole thing is 0 and everything is 0.
Yeah.
So we're good.
So yeah, the only thing you might be concerned, or I would be concerned about is explaining why exactly the derivative is the derivative of the first thing plus the derivative of the second thing. But that's just kind of, you can prove it by linearity. If you write down the limit definition, say of the derivative or something like this, you can verify that that has to be.
Okay. These are the things I want to do. Okay, so maybe
So, okay.
I'm allegedly supposed to rewrite everything.
I don't want to spend much time on this. There's less second years than I thought there was. So I think for the third years, this is like mostly review some new language, but otherwise it's the same. Yes.
That's actually more interesting because again the textbook we use is kind of done in a more convenient way.
Yeah, I mean this is actually also very handy.
Yes.
And the paper that I am referencing, the whole premise of that paper is to argue that Hilbert spaces are a really shitty way to formulate quantum mechanics. And this came out in 2024, and I haven't read it. I don't know how credible these people are, but they kind of make an interesting argument. And one of their arguments is with this whole completeness thing, that even if you have completeness and you specifically want to for the Hilbert space, like there's some problems that you can have some quantity be convergent in one reference frame, but then if you move to another reference frame, this quantity can diverge. And so this is actually not the best. And so actually maybe even working with wave functions is nicer, because then you can like start talking about like restrict your space even further. Like there have been suggestions that instead of talking about L2 wave functions, maybe we should only be talking about Schwartz wave functions. And so Schwartz functions are the set of functions which they go to 0 at infinity faster than any polynomial, or is it exponential? Yeah, like they go exponentially fast at infinity, and you kind of need that to have any multiplication operators by x have convergent average values. But okay, that's something later. So let's apply what we've learned and apply it all on one example, because we've just given a bunch of abstract postulates. So let's do one example. I'm just going to say words for you.
Yeah.
I'll say words for you.
I would definitely, because I spent my afternoon basically rewriting the entire thing.
Perfect. You should say what postulate we have, and so the first postulate is this, and so this is what will correspond to this postulate, and maybe think physically why.
So the sum of our problem is we have this potential, and this is just going to be our coordinate. So this is a one-dimensional box. We go from 0 to L. Things are good. Okay.
And what's in this box?
A particle.
Okay. What are we trying to do?
Wave stuff.
No, what are we doing? A physical thing, not wave stuff. particle in a box, so we're trying to write a quantum mechanical model for.
Particle in a box.
Okay, there we go.
You have to know hard questions.
That's over.
Okay. So is there a particle? Okay. Okay. So if we're measuring stuff like location. Okay. I'm just gonna define the space first. Okay. So this is going to involve P1 stuff. We want some kind of vector space and vectors to represent different states of the particle. So we're going to use L2 space as you were literally just talking about.
Right figure.
My bad. What am I doing? Okay. Functions from 0 to L to the complex numbers. Such that, maybe I'll do the bar here. Okay. Such that the integral of the function squared over
Absolute value squared
is
just right less than.
okay. And then we also have f of 0 is equal to f of L is equal to 0.
So the second condition is just so the particle doesn't leak out of the box. Right? And in principle, I could think of this as a wave as a function not from 0 to L, but a function of all of R, but that is just 0 outside of the box. Okay, that's still a vector space. That's fine. Right. We have some inner product defined on it. So yeah, the other question is, how do we know that for a particle in a box, the right Hilbert space for it is these L2 wave functions, and this is the right way to go about this? I'm actually not sure about how historically they've kind of come up with this, but I think this is kind of one of those, you can figure out that this Hilbert space should be this one kind of from experiment. Really, like this is more of an experimental fact that this is the Hilbert space that you work with, and then gives you the right answers. But yeah, this is the other thing that in quantum mechanics, oftentimes you don't actually know what the Hilbert space you're working with is, but you maybe know what the operators have to be, and maybe you know some of the computations between the operators, but you don't know what the Hilbert space that they're acting on actually is. And so then there are various procedures for how to figure out what at least a part of the Hilbert space should be based on just the commutation relations of the operators and the Schrödinger equation. So, this example is kind of very unrealistic in the sense that we actually know what the Hilbert space is. Oftentimes we don't know what it is, and we have to figure out what it is. Like is the case, for example, in like every quantum field theory. In the quantum field theory textbooks, that's kind of a part of it that all you know is what the Hamiltonian is and the commutation relations between like P and X, let's say. And then after that, you have to figure out how this Hilbert space actually looks like and how my Hamiltonian would even act on this Hilbert space. And that is often, not immediately obvious, but there's some standard ways to do it.
Okay. We're going to use the second postulate, which is, and just read out the next one we were working.
And the other problem sometimes even with the Hamiltonian is like in condensed matter, right? You have some many body system, you have like a lot of electrons, you don't quite know how exactly they interact. And so in like condensed matter physics, even your Hamiltonian is usually approximated in some way. And then, everything you have to figure out from scratch, you don't know it. You have to give some approximation for it, and then you get perfect. Or maybe you get good results. If you're a good physicist, you'll get good results.
Okay. We're going to define momentum observable and the Hamiltonian.
Yes, go ahead.
Okay. So momentum is going to be negative IHR partial x.
This is an operator from L2 to L2. Well, that's
What do you mean that's a lot?
well. I can come up with some integral functions I can have an L2 function which I take a derivative of. So, right? Yes, exactly. So
I'm
This is
upset.
not. This is not. This is where all this starts getting heavy. This is not really an operator, but it is nice. And this is why we want short spaces sometimes, because then it should be fine.
Okay. And then I go, aha, energy. Kinetic energy is momentum squared.
What is
Fine, Hamlet.
classic? Yes, p squared over time. So it should be the same thing here, quantum mechanics. Sure.
Nothing
And
could
okay, here I will make another lengthy comment. So usually we know the Hamiltonian for a classical system. So you know how a particle evolves classically, right? It's just the Hamiltonian is p squared over 2m. And you've not taken physics 354, right? It doesn't matter. The point is that in principle, if you want to figure out how my classical system evolves in time, so I have, let's say, Newton's equations, right? And Newton's equations gives me some vector field on my space, and then so in the classical case, the state of my system is fully defined by the position of my particle and its momentum at one given time. That fully determines the state of my particle. So the state of my particle is this q comma p space. And Newton's equations, they give you a vector field on this q p space, okay, where q dot is equal to p and p dot equals to q dot is equal to p over m, and p dot is equal to minus the force or whatever. And this gives you a vector field. And so over time, your state evolves kind of flowing along this vector field. Okay. Where was I going with this? Yes, and so in classical mechanics, the state is this position and momentum, and then it somehow evolves over time. How do we figure out quantum mechanical things from this? There's a procedure called canonical quantization, which I will not talk about in too much detail. But the idea is that the Hamiltonian should be symbolically the exact same as the classical Hamiltonian. So if I know how my classical system evolves, and I know the Hamiltonian for it, this Hamiltonian is right. That's what we say.
Like we in the last few chapters was referring to some like Lorentz theorem. Like says that like averages behave classically.
Yes. I think it gives that, but not quite. So this is a consequence of what I was saying. Sorry. Let me start over. I was being. So I have my states, which are position and momentum, and then it turns out the classical Hamiltonian contains all of the information to tell me how these states will evolve over time. And so the point is that if you want to write down a quantum mechanical Hamiltonian, then canonical quantization is this procedure which tells you that you should just take the classical Hamiltonian, and wherever you see a p, replace it with that, and wherever you see an x, replace it with a multiplication operator by x. So what it's saying is that if you know the classical Hamiltonian, you can write down some quantum mechanical Hamiltonian over this L2 space. And the way to do it is just to replace p with minus I bar partial x, and to replace x with multiplication of the wave function by x. And so this is what's called canonical quantization, where you just take the classical thing and make it quantum mechanical just by writing the same letters, but now the letter p means I bar partial x, or minus I bar. Okay? And Ehrenfest's theorem is a consequence of that. That if I just write down the same Hamiltonian in the quantum case, but with the same letters, but now the letters just mean very specific operators, and then compute expectation values, then the expectation values will behave along the classical equation of the motion. It should, well, not quite always. I think there's some condition on something varying slowly enough or something being smooth enough. I think it's almost true. Because I can imagine you can have some very large fluctuation for no reason and then something weird happens. time because it's a free particle in that box. Okay, sorry.
Okay, anyways, what was I? So then you do very basic math, and then
So what do we want to find out?
sorry,
Let's try to finish up in 5 minutes. What do we want to find out?
well, I immediately went to finding eigenstates, and
What do we want to find out? What is the Hamiltonian?
energy.
Energy. Okay, so we want to find the energies that we can measure in our system. The energies that we can measure in our system should be the eigenvalues of this operator. Okay, just tell me what the eigenvalues are and what the associated eigenvalues are.
Sure.
Give me the answer.
So E sub n is, where is it?
One over n squared or n squared? I don't know.
Yeah, n squared pi squared
Yeah.
h bar squared over 2ml squared.
Okay, good. So n squared.
And then this will be
H bar all of this.
2 over L. Fine.
Yes.
With this is without time dependence.
Yes. Okay. And so now, in principle, the ideal case would be if I had some more complicated initial state, I can express it as a sum of some signs, and then I would evolve it along using that formula. Okay. Yes. So it's kind of surprising actually that you put a particle in a box and all of a sudden the energies I can measure are discrete. That's like physically like why did this happen? The other thing is, okay.
I'm just writing the time dependence.
Yeah. Okay. And then you have nothing else.
I have a back page.
What is it about?
Let me see if there's anything useful. It was just like
Oh, the multiplication.
calculating like probabilities and shit.
Oh,
yeah.
Forget about it. Right. So that's good.
And, like adding a potential.
Yeah, right. So I'll just mention this very quickly. So if I wanted to add a potential, right, canonical quantization says what? So if I have a classical Hamiltonian, it's p squared over 2m plus some potential. This is just classical. My argument is that the quantum mechanical Hamiltonian will be the exact same thing. But, okay, p squared is this composed with itself twice. And now v of x, this is something that maps a wave function to the wave function multiplied by v of x. So this is like a multiplication operator. It's just that people are too lazy to write down multiplication operator. I think some people denote this as like some Cyrillic m with like v of x like this to mean that I'm multiplying by v of x. Okay, but no one writes this, and everyone just writes v of x like this. And what it does is takes a wave function, multiplies it by v of x, I get a new wave function. Once again, this actually might not be an L2. This is not actually a good operator. So this whole L2 business.
The second you do that's not even L2 anymore, is it?
Yeah, exactly. If this is not very, very nice, this will not be an L2. This is not actually an operator over L2. Neither is this, which is why we should really be working with a completely different space. Don't think about it too deeply. No one cares. Oh, I'll change the space. Who cares?
I just want to make sure one thing. So in this example, because like the v is not changing as time evolves, so we can use the separation variables to like solve
Yes, because h is not changing in time, correct. I can use separation variables. If h did change in time, well, we'll get to see that later. But well, it's actually, so I guess for you, you may notice that hold on, the Schrodinger equation is just a transport equation. So actually, you can think of, you can write down the Hamiltonian, you can think of as a connection on a line, not line bundle, on a bundle over R, where the Hilbert spaces are, sorry, where you have a line which is time, and then you attach a Hilbert space at every point in time. H your connection, and evolution in time is parallel transport with time using h as a connection. You will learn what all of those words mean by the end of this semester. Okay. But okay, that's just fun. Right. If I wanted to add a potential, I would then add to this multiplication operator v of x, and once again try and find the eigenstates of this and eigenvalues to find the energies. And so that's exactly what you have all seen, because all you have taken a quantum mechanics course in the finite square potential well, you just find functions that are eigenstates of this everywhere, and okay, that's how you get the energy eigenvalues. Is there anything else there that I want to say? But yeah, so yes, so this procedure, canonical quantization, is very important. Why? Because okay, with p squared and v of x, it's kind of easy how to do this. But when you start trying to introduce the electric and magnetic fields, right, that becomes a little complicated. And there you need more information. Where essentially the information is in Hamiltonian mechanics, there's this thing in geometry. There's this thing called Poisson brackets, which maybe you've seen. Okay, there's this thing called a Poisson bracket of two functions f and g, and this kind of okay, I will not say exactly what they mean, but they have some very particular physical meaning and some very particular geometric meaning, which I could explain if I had, say, 20, 30 minutes. Actually, maybe you will explain it next week. And the point is that, okay, you can compute these for some two functions f and g in the classical case. And the point is that in the quantum case, whatever this was, suppose this was some number. In the quantum case, the canonical quantization says that I have to take whatever Poisson brackets I have, and I replace them with commutators. And now these things, after they get promoted to operators, their commutator has to be the same as the Poisson bracket was previously. And this becomes very important in working with anything that you know I don't know is P and X. There's some things like the magnetic field or not the magnetic field, like the electric field. You wouldn't necessarily know, how it would act as an operator. That wouldn't be obvious. But then using this stuff, you can figure out how it should commute with P and X. And if you know how the electric field should commute with P and X, well, then you are in business, and you can maybe try and compute something with just the commutators later. But yeah, this is why commutators are important in quantum mechanics. Sometimes you don't know how the operator acts on the space, but you know how the operator commutes with other operators, and maybe you know how the other operators act on the space. And so using commutators, you can extract some information about how this new thing acts on it. And then the commutators, you can figure out what they are from the classical case using this procedure of canonical quantization. But you guys don't even know what this is, so it's kind of hard for me to explain. It's not, I wouldn't say it's a postulate. It's a way of figuring out what all of the things are, but it's not the only way to do this, and it's one of the ways to do this, and it's kind of like, it's a procedure which sometimes works, usually works. Not always. I wouldn't call it a postulate. It's just a way to figure out what the quantum system should be from the classical system. So then you have all of these questions of like, okay, if I have a quantum system, does it always come from a classical system? And okay, it doesn't. And a bunch of other things. But yeah, canonical quantization is just a way to go from the classical system to its associated quantum system. And it essentially says, write down the same letters, but now p's are this and p's are this multiplication. Roughly speaking. Not exactly, there's more caveats. For our purposes, that's good. And that's really what we're doing in this particle in a box case. We know how a particle in a box should behave, right? What the Hamiltonian should be should just be p squared over 2m. And then I use this canonical quantization procedure to do this. And I now have an operator. Now that I have an operator, I can use the postulates to compute probabilities, to compute what I can measure in my experiment, and all these other things. Okay. okay, I guess for people who have taken physics, yeah, actually, let's make a small comment. So H is an observable. We found eigenvalues and eigenfactors. P we said is also an observable. Question: can we find eigenstates and eigenvectors for P or a particle in a box? You can answer. No, we cannot. I don't think I will have anything that will satisfy it for this. So I shouldn't be able to. So there's two ways of.
You want like explicitly regular optics, or you want?
So I want to. You tell me, will I have some particular L2 function, which will be an eigenstate of this? On. So the point is that you won't be able to write it down because of the boundary conditions. You will get that. So the eigenvectors of P will have to be e to the I h bar negative or not negative. Yeah, minus I h bar x. Do you agree? These have to be the eigenstates because this solves the differential equation. Okay, but you want this to be 0 at 0 and 0 at L. And so you will fail. So this actually doesn't have eigenstates, even though it is symmetric and whatnot. This will not have eigenstates for this particular L2 system. For the people who know physics in the room, which probably everyone, but why physically should this not have any eigenstates? Remember that so an eigenstate means what? Means that an eigenstate with eigenvalue p means that I measure exactly momentum p. Right? If I have this eigenstate, that means that state has exactly momentum p. Okay. But what is something that Heisenberg told us? That we have an uncertainty principle between x and p. And so that if I'm very certain in x, I have to be incredibly uncertain in p. Do you agree? However, the problem is a particle in a box implicitly gives me the condition that I have to be between 0 and L. Okay? So this says I have this Heisenberg uncertainty principle has to be h bar over 2, maybe there's some pi's or whatever. But this fact immediately sets the uncertainty in x to be L at most. Do you agree? So delta x in this case has to be equal to L at most. And so this means that you see that delta p has to be greater than h bar over 2 you agree? So just kind of from this simple argument, you see that in a particle in a box you cannot have an eigenstate of momentum because otherwise you're completely certain in your momentum and not really certain in your but you can have an eigenstate of position. That's okay. What are the eigenstates of position? Well, eigenstates of position which are in L2. Do people very vaguely remember what the eigenstates are?
A function.
It's a function that's not a function, it's a delta function. You guys have heard of delta functions, right? So one way to think of a delta function is as an eigenstate of momentum. So x multiplied by this multiplied should be this degree because this is in some sense infinite at x naught and 0 everywhere else. So these two things should be. So you can think of eigenstates of delta functions, eigenstates of position. And so there should be some way for me to rewrite my function psi as a sum of eigenstates. And I can do that. I can write psi of x equal to an integral of psi of x naught delta x minus x naught, and then I have to integrate with respect to what? With respect to dx naught. Do you agree? And if I do this, you can see that this is kind of like a linear combination of my delta functions multiplied by some constant number, and then just summing over the x naughts. Do you agree? So this is like rewriting my wave function in the position basis of delta functions. Okay? So that's one way. Another way to think of a delta function as an eigenstate of the position operator. Of course, it's not a delta function, and well, it's not a function. It's not. But this is a vector in some space, and so that maybe our Hilbert space should be that space instead, and I have inclusion maps. Don't worry about it. No one cares. Like, well, some people care, but it's not that important. For our purposes. Okay. I guess if yes. Is this at all helpful or new for you?
Well, it's not new, but it's like super recent.
Okay. Well, okay, good.
Actually makes it clear.
Yeah, okay, exactly. Like, if this is at least a little more clear, that's good. Okay, but once again, this can be made rigorous without me changing this line whatsoever. I just need to change the words I say, but to change the words I say, I need to scale up models. And we're at 8:33, so we should stop there. Okay. But in principle, if you're doing quantum mechanics, you have some Hilbert space, you have some operators, you compute the eigenvalues of these operators to figure out what it is you can measure, and then you figure out somehow what your initial state should be, and you can figure out what the probabilities of your measurements should be, and you do it using these postulates in this kind of organizational scheme. I have some exercises from last year, which may be interesting for people to look at, because even if you're in physics and statistics, you may have not seen them before. There are no solutions. I will never write solutions because I don't have time. Ask these two if they've done the exercise.
Right.
Yes. Yes.
So in this specific case, we cannot like see the Fourier transform in the right?
Well, you can always write down a Fourier transform. The problem is then these e to the IPX, this doesn't make sense. Actually, so what is a Fourier transform in this case? I told you just now that P applied to minus IH bar PX is P minus IH bar PX. Do you agree? Or well, minus IH bar. Actually, no. There's some. So it should be H bar squared, right? If I apply P to this, I get H bar squared P. Do you agree? No, but I had a minus I, P had a minus I, so it cancels out. Doesn't matter. This is an eigenstate of P. In principle, if we didn't have these boundary conditions, if we were looking at it kind of over R, okay, then it's not an L2. Stop complaining. It's an eigenstate. Good. If it's an eigenstate, what can I say? Well, if it's an eigenstate, then have some basis. Okay. So I should be able to write things out in the basis of momentum. Okay. So whenever I do a Fourier transform, I'm erasing what I'm about to say. If I do a Fourier transform, what is a Fourier transform of a function? The Fourier transform psi k of psi of x is what? Psi of x e to the minus IH bar px. Maybe there's some other things. Sorry, not pk. I'm using k for some reason. Kx. dx. Do you agree? Yep. But what is this? Does this have to have a bar over it? I think it might need to have a bar over it. It doesn't matter, but let's put a bar over this. What is this? This looks like the inner product of this with this. Do you agree? Yep. So this looks like the inner product of my function psi with an eigenstate of momentum. Do you agree? So all the Fourier transform is just rewriting what function is in a basis of momentum eigenstates. Why? This is what the inverse Fourier transform is. All it tells you is that these are the coefficients in the linear combination. I can express psi of x as a linear combination of e to the minus I a bar kx with these as the coefficients. So, or maybe plus or something. I forget exactly. The rough idea is that the Fourier transform is just a change of basis to momentum space. Yeah. And this is the coefficient in front of this vector, and I add up, and I sum over these vectors with these coefficients. Okay, there are some factors of I and H bar which I'm not including here because I don't remember them. So that's fine, but the idea is that the Fourier transform psi of k, this should be k, and there should be dk, sorry. The Fourier transform of psi of k is really the coefficient in front of the energy, the momentum eigenstate when I expand psi of x in this momentum basis. That's like the physical way to think about it. It's just a change of basis, but instead of a sum, I have an integral. Okay, so that's it. Okay, we've been here long enough. Thank you.